Welcome. This is Professor Nathan Weezy of Marquette University. This section we're going to talk about a proportional controller in the digital domain. The proportional controller is one of the simplest controllers. In equation 1 here, I have the transfer function. It is simply k. K is some variable that we have to find in order to make our system stable and achieve the objectives that we would like to achieve. Let's assume that we have some plant. And the plant is equation 2, 2 over z times the quantity z minus 1. And let's essentially assess the stability of this system. So we have a plant, we have a controller, there's no gain in the feedback. Let's take a look at the feedback path and how stable a system will be. So let me quickly sketch what I mean here. So we're going to have GP, we're going to have GC, and that's literally it in this control loop. So those will feed into each other. This will be the output. Let me scoot this over here so I can draw this better. So we'll have some reference that'll come in, and then we'll feed that back. So this is our control loop. The plant here is equation 2. GC is equation 1. Okay, so what we're going to try to do is assess the stability of this as we sweep K. So first we're going to calculate GOL. Of course, GOL is just GC times GP, right? That's GOL, the open loop gain. And then, of course, we're going to calculate now the closed loop gain, which would be equation 4. Well, closed loop gain is pretty easy to get in terms of the open loop. That'll be GOL over 1 plus GOL. And you will land at equation 4. Now, how are we going to assess the stability as we sweep K? That's really simple. We're essentially going to find the poles of the denominator, or the zeros, excuse me, the denominator, which are the poles. So we'll solve this equation. Of course, it's just a quadratic, so we can solve this pretty easy. And we do that in step 5 here. Here are our poles. Okay, so essentially when I look at this, for instance, if K is 0, it looks like we're going to have a double pole at, we'll have 2 poles, one at 0 and one at, looks like 2. So it'll be unstable with no gain. Interesting. Okay, so you're basically going to have two poles here, and as you sweep K, they're going to start at real values. So let's go ahead and see what they are. In fact, I have them up here on this pole 0 plot. So we have 2 poles. One starts over here and the other one starts here. So this should be a K of 0, because then we'll have 1 and we'll have 0. Now as we increase K, what's happening are these poles are going towards each other until one point where essentially it looks like the point that they're equal is K is equal to 1/8, I believe. Yeah, you'll have a double root at 1/2. So you can see this is at 1/2. And that's when K is equal to, I believe, 1/8. And then once you increase after that, your roots now become complex conjugate pairs, and they shoot out like this, which is interesting because what this is saying is essentially we're going to be stable for a lot of values of K until they cross this boundary of the unit disk, the circle. So right here, whatever those K values become, I'm not sure what they are yet, but once we pass that, our system will be unstable. And everything in here will be stable then. And another note is as long as both your poles are on these 2 lines, let me use a different color here. As long as these poles are on these 2 lines, you're going to have a nice damped response because that line is where the damping ratio is 1. But guess what? As we increase K and they start to work out on this trajectory, you can see here, like if we were here, for instance, and here, this is the line for damping ratio of 0.9. And as we increase, we could have, for instance, we could be out at 0.5, right? And it'll get less and less damped. It'll have more and more ringing until essentially we get outside the unit disk and everything blows up. Okay, so let's take a look. So it looks like I went ahead and solved this, yeah. So essentially, when these numbers go above that, so yeah, I solved it. It looks like what I have here is for a K less than 1/2 that'll be stable. So right at 1/2 is this point here, and this point here. Okay. Okay. Let's pick something arbitrarily. We'll have a K of 0.1. Let's see what happens. So we'll plug that in for a controller. We plug that into our closed-loop response in equation 9 and calculate the roots of the characteristic equation, or the denominator. And what we get here is a 10, equation 10. And you can see we have two real roots, 0.7 and 0.27. 0.7 and 0.27. Let's go see if we can put these on here. 0.7 and 0.27. 0.7 will be somewhere here, and 0.27 somewhere about here. So those are our first two poles. So we expect a nice response because the damping ratio is perfectly 1 here on this line. So if we plot the step response, we get this. Just a nice, good, clean step response. Goes right up to our trajectory. Okay, cool. Let's try a different game. Let's try 0.4. Now remember, once we go past 0.5, the system's unstable. So this is going to be close to being unstable. If we plug that in for a controller, calculate the closed loop response here in equation 12, and then essentially we calculate the poles, which are the roots of the denominator, what we get is 13. These are our poles. So we have plus 5 and plus or minus 0.7. Let's go look where those are. We'll do a different color here. Plus 5 plus or minus what did I say here? 0.74. Okay. So that's going to be somewhere right about here. Let's use a different color. So 0.7 somewhere about here. And let's see, this is a half, somewhere about here. So now you can see that damping ratio is like 0.15, something in there. We're pretty close to the unit disk circle. And if we go ahead and give it a step response for that, this is our output. And what you can see here is this rings for quite some time, and then it settles down. And this will get way worse if we get closer to that unit disk circle. Another thing I'd like to point out here is that if we go up here quick and we look at, you see this trajectory and these lines here, this says 0.3 pi by t. So 0.3 pi by t. That's actually the natural frequency here. And what this will tell us is essentially tell us what frequency this thing's going to ring at. So when we look at this, this is going to be 0.03 pi divided by t. And that's our ringing frequency. Okay, that concludes the proportional digital controller. Thank you.